Hey everyone, welcome back. Today I want to talk about state space modeling, or really the intro to state space modeling, with an example. So this applies to power converters, obviously, and maybe this aligns more with like conventional control techniques and control literature, as opposed to maybe the more simplified approach that's often taken with power electronics. So the benefit of state space modeling is that we can really cram a lot of information into something that looks relatively simple. So typically with state space modeling, we want our control systems to look something like the form x dot equals ax plus bu. And then we usually talk about the output as y, and maybe we say this is cx plus du. This is like the standard form, right? So x is a vector which contains your states, or the variables of interest. Right? So for our cases, this is going to be stuff like IL or VC, that kind of stuff. So like the state variables of our passive elements, the variables of our passive elements. So how do we get our converter into this form? Well, it turns out we do something relatively similar to what we've done before. It's circuit analysis, right? So we divide our circuit into two states, or into the number of switching states, or write equations for all the models, and then basically plug it into this form. And just as a heads up, it's gonna look a little bit different than what we've seen before. So typically, this is like in regular control literature, this U is like our control variable, or the input to our system, right? So if we think about a regular control system with a plant and then some kind of controller, usually this is what we're referring to. So maybe this is like our negative feedback, right? And then we have some reference, and this is U. This is usually what the control systems in literature look like. This U is kind of like the input to our controller. However, here we're going to use a slightly different convention. So instead of referring to this U as control, so this U is going to be our exogenous input. And I decided to use that word because it sounds super cool. So really this is an input that isn't our control input, right? So in this case, it's going to be things like VG, right? Independent inputs, right? So variations in I, that kind of stuff. So that this is an EG, VG, like I, things that vary with the system that aren't our controller, right? So we're trying to typically control the output voltage. That might be our Y, right? And our control input is actually D. For pulse width modulated converters, right? It could be F for other converters, but for this specific example, it's going to be D. What we're going to do is draw out the circuit in each switching state. We're going to write our differential equations for each of those switching states, right? So I'm going to be careful here, because state is used for a few different things, right? So switching state, the state of the circuit itself. A state variable is like IL and VC and stuff like that. So each switching state / variable, right? And this is the same as what we do before, except instead of doing IVSB and averaging out completely, we keep it as a differential equation. Then what we're going to do is basically, we are going to average, and perturb it, and then linearize, right? And that is going to come up, that is going to allow us to generate our state space model, our small signal model for the converter. All right, guys, so let's do an example. So what are we doing here? We're going to look at the buck boost with losses. So what is the buck boost? Well, this is the inverting buck boost, to be clear. And it looks like this. And what we're going to do is we're going to include some losses for the main switch and the synchronous rectifier. So for MS, it's going to have a resistance R1. For SR, it's going to have a resistance R2. And that's all I'm going to include. This is just to like describe to you how to do this thing. So what do we got? We also have L, we have C, we have V out over here. This is RL, this is VG. And then if we think about the variables, the state variables, well, the variables of interest we have are VL, IL, VC, which is V out, and IC. So, how do we do this? Well, we have to define our state vector, X, which in this case is going to be IL and VC, right? Our U vector is just going to be VG of t. This is our other external input, right? Duty is also an external input. That's what we control. We'll see how that is integrated into this system later. And then our output, we can think about our output, is just going to be V out of t, right? And this is actually equal to VC of t. And if you want to write it out in this specific way, we can say that we pick out VC from our state vector. Cool. Well, we write out the circuit in each switching state, right? So let's do that first of all. So in the first switching state, MS is on. And in the second, SR is on. Right, so if MS is on, then we have R1 over here, right? Because we said that the switch had some on resistance. And it looks like this. In the second switching state, we have something very similar, except MS is off, and instead we have R2. We have VG over here. We have V out. This is R1. This is IL, VL, VC, IC. And very similar over here, right? I wrote RL. This is R1. This is R2. This is VL, IL, VC, IC. This is RL. Our load resistance is RL, and we have V out. So let's start writing our equations. So over here, what do we have? Well, we want to write out the equation for VL of t. VL of t is simply L di dt. Right? In this case, the voltage across the inductor is going to be equal to Vg minus IL times R1. The current through the capacitor is equal to C dVc by dt. Here, IC is going to be equal to minus V out over RL. Over here, in the second switching state, we have something very similar, right? So we want to look at the voltage across the inductor. The voltage across the inductor is actually equal to L dIL by dt. It's going to be equal to, in this case, well, we have V out minus IL times R2, or VC in this case, VC. Right? We want to keep it in terms of the state variables. And again, the current through the cap is equal to the derivative of the cap voltage times the capacitance, and the current is going to be equal to minus IL, right, minus VC over RL, right? This should be VC. We want to do it in terms of the state variables. And then here we can say that Y is simply equal to VC, Y is equal to VC, right? So recall, we're actually trying to turn this, this system, we want to get to an equation that looks something like x dot is equal to AX plus BU, right? And then Y is going to be equal to CX plus EU. This is what we're trying to get, right? And we're almost there. So we have a set of equations, right? Which means we can turn the set of equations into a matrix equation, a single matrix equation, right? Well, we kind of have two, right? So we have this set that we're interested in and this set that we're interested in, right? So let's write these out as matrix equations. DIL by dt is the derivative of the state variable IL. dVC by dt is the derivative of the state variable IL. Our state vector is x. The derivative of the state vector is x dot. So we're multiplying x dot, which I'll just write like this, DIL by dt, dVC by dt. We're multiplying it by something, right? So this first equation, this top row, only has to do with DIL by dt. There's no dVC by dt. So that means that this must be 0, this term must be 0, this entry must be 0, because we're not picking this out for this equation. Meanwhile, DIL by dt is multiplied by L. For the second equation, there's no DIL by dt, so this entry must be 0. And we simply multiply dVC by dt by C. This is equal to, well, we just convert this into a matrix form, right? So again, we think about what we have to multiply the state vector by, IL, VC, to get this equation, right? So this first equation, we're multiplying IL by R1. So we want to multiply IL by something, we should put minus R1 over here. There is no VC in this equation, so this entry must be 0. The second equation, there's no IL, so this term must be 0, and we're multiplying VC by minus 1 over RL. So this is our second equation, or our second matrix. Then we have to add in our exogenous variables, our U, right? So U, in this case, is just VG. So I'll just write VG here. And because we have two equations, we should have a vector with two entries, right? So in this first equation, we have VG in the first half, right? So we have 1 here. And then also, in the second equation, there's no VG, so there's a 0 here. Over here, we do something very similar, right? Again, these two equations, the top one only has to do with DIL by dt, the bottom one only has to do with dVC by dt. So the first matrix looks identical, right? Now, the next matrix, this is relating our state variables, right? So IL, VC. What do we multiply our state variables by to recover these equations? So in this first term, we have VC and we have IL. So we have minus R2 to get IL, to multiply by IL, and we also have VC, so 1. Down here, we have VC and RL, right? So over here, we want a -1 for IL, so we should put -1 here, and multiply VC by -1 over RL. And then, again, our exogenous variable is VG. Well, there is actually no VG in either of these equations, so we have a 0 vector. Great. So these are our two equations, and we can also include something for y, right? So in this first term, y is going to be equal to, well, it's just going to be equal to VC. So what do we have? We want to pick out, this is a single variable. We're multiplying it by our state vector, IL, VC, and we only want VC, so the matrix that we multiply it by is 0, 1. Similarly, over here, y is going to be equal to 0, 1, IL, VC. Great. And there's no VG. There's no VG in the y term, right? So we don't have to include that. So now, how do we average this? Well, we do it in the same way we did before, right? We're just going to weight these by the time they're on and sum them together, right? So this is going to be multiplied by d. All this stuff is going to be multiplied by d. And all this stuff is going to be multiplied by d prime. And then we simply sum them together. So what do we do when we get that? Well, over here, we have this matrix. So I'll just write it out. So we have d times L0, 0c. Now let's write this as x dot plus d prime times the same matrix times x dot. And then on the right-hand side, this is going to be equal to d times minus 1, 0, 0, minus 1 over RL times x plus d prime, this matrix, minus R2, 1, minus 1, minus 1 over RL, x. And then the exogenous stuff, right? So we have d times 1, 0 VG plus d prime 0, 0 VG, right? And then we can do the same thing for y. In the end, what we get for y is going to be equal to 0, 1 times x. And that's it. Okay, so let's group this stuff together. What I'm going to do is actually just rename this stuff so it looks more canonical, let's say. So this thing, this is what we call K. Notice it's the same for both states. This is A1. It's the A vector for the first state. This is A2. It's the A vector for the second state. This is B1. It is the B vector for the first state, or the B matrix, and this is B2. It is the B matrix for the second state. So if we write this all out, what do we get? Well, d plus d prime is 1. So we get k times x dot is equal to d times a1 plus d prime times a2 times x plus d times b1 plus d prime times b2 times, in this case, vg. And then we can rename this. We can say that this is equal to A, and this is equal to B. So let's define A and B. A is going to be equal to minus dr1 minus dr2 in the first entry, minus d prime in the second entry, minus d prime in the third entry, and minus 1 over RL in the fourth. B is simply going to be equal to D and 0. If we think about it, we've actually written our equation in this form. Kx dot is equal to AX plus BU. We've done it. This is our, let's put it down up here. This is our state space equation. How do we use this? Well, let's look a little closer. Well, think about steady state. This is steady state, not small signal. In steady state, x dot should be equal to 0. If we do this, then we get an equation. 0 is equal to ax plus bu. What does this mean? It means that x, our steady state solution, maybe I'll write it as capital X, is equal to minus A inverse BU. Right? So using this matrix form, we can find a solution to all the DC components of our system. So what is A inverse? Now we can basically solve x, right? For x, we can say that it is equal to minus, I'm going to factor out this d prime as well, right? So minus 1 over d prime squared dr1 plus d prime r2 over d prime squared RL minus 1 minus 1 over RL d prime, there's a minus, oh, I've included the minus sign, minus dr1 minus dr2, right? So this is A inverse, then we have B, which is just D and 0, and then U in this case is just VG. right? And if you multiply this out, you'll get minus d over d prime, and then this extra factor, which is kind of what we expect before for vg, or for v out. And then for IL, you're going to get d over d prime squared over RL, and then also this factor, right? So hopefully this kind of makes sense, right? So this is the DC solution to our equation. But the DC solution isn't the only solution we're interested in. We're also interested in the small signal solution. So we can perturb and linearize our equation, right? So writing this out, we can write this out more explicitly. So we had kx dot is equal to, I'm just going to write out including d's, right? So we've averaged, but I want to include these d's again because we're going to perturb the d, right, to get a small signal component. So we have d a1 plus d prime a2, right? So this is like our a vector times x plus d b1 plus d prime b2 times u. This is our b vector. Now let's perturb it. If we do that, what does that mean? It means that x is going to big X plus small signal x. D is going to go to big D plus a little d. D prime is going to go to a big D prime minus a little d prime. And U is going to go to big U plus little u. All right, so if we apply this, and we turn our dot notation back into d by dt just for convenience, we're going to get d by dt x plus little x is going to be equal to, cool, so if we expand this out and note that the derivative of a constant should be 0, then we can see the following. We're going to get k d by dt of the derivative of the small signal component, and that's going to be equal to a times big X plus little d times a1 minus a2 times big X plus a times little x plus a1 minus a2, two little components, right? And then for the u part, we're going to get b times big U plus d tilde times b1 minus b2 times big U plus b times u, and then also we're going to have b1 minus b2 little u and little d. So what we can notice here is that we have a DC component. Then we have our first order terms, or our linear terms, right? And then we also have our higher order, second order terms, which are nonlinear. So for our small signal model, we can ignore this, and we can ignore this, right? We're only interested in the terms with a single small signal component. And we can write this out. K times, sorry, I have an x, I have a dot here, I don't need this dot. Let's ignore that dot. Dx by dt is equal to a little x plus b little u plus, now our big term, a1 minus a2 times big X plus b1 minus b2 times u times little d. And this is kind of like a canonical form that we can use, but maybe to simplify it, we can define this as m, just for convenience, right? So in this case, our m solving gives us IL times minus R1 plus R2 minus VC plus VG, right? And this is a vector with two components in it, and that kind of makes sense. X, which is big IL and big VC, we've solved for it just before. and it is equal to dVg over dr1 plus d prime r2 plus d prime squared rl, right? So this is like IL, and then this is equal to minus dv prime rl dr1 plus d prime r2 minus d prime squared. Sorry, so this should be minus up here. RL times Vg. In any case, this brings us to a specific point, right? The specific point is that d is our control variable, right? So from the state space model, really it's giving us an option to decide what d is. And often for these closed loop systems or control systems, they'll set d to be equal, somehow related to our variable x, right? And doing that allows us to solve for what the closed loop system is. We can do like a pole placement method, right, to figure out where the poles are and drive our state variables to the place we want to drive them to. But I won't do that now. This is really just to introduce how we get our converters into this form, and this is how you do it. I hope that was helpful. Cheers.